So let's talk about the lens equation. The lens equation allows us to do geometric optics, but in a quantitative way. Now, it will turn out that it works exactly the same way for lenses as it does for mirrors, just like geometric optics does. So I'm going to spend most of my time talking about lenses because they're easier to draw the diagrams for. All right, so we've got a diagram like this for a converging lens. Now, remember the principal rays. We've got coming in parallel out through focus. Remember that the focus is on the proper side of a lens when it's converging. All right, then we've got straight through the vertex, no problems. Then we've got in through the kind of wrong focus and out parallel. The guys all meet. There's my image. Everything's wonderful. Now, the way that we're going to name things on here so we can have an equation is DO is the distance that the object is along the principal axis from the vertex. DO, distance, the object from the lens. All right, what about DI? That's the distance that the image takes from the lens, again, along the principal axis from the vertex. And then F is the focal length. So that's the distance from the vertex that the focus is on the principal axis. All right? So just like before, we'll draw the little diagram and put the x's at the focus on either side. Now, the lens equation says that if you do 1 over DO plus 1 over DI, you get 1 over F. You have to be very careful with this equation because it really means 1 over. You can't do DI plus DO equals F because it doesn't. Okay, that's never true. All right, so you need to be careful with that. But once you are, it's not that difficult to use this equation. The only kind of strange things are what does it mean when DI is positive versus DI is negative? If DI is positive out of this equation, then what it means is that the image appears on the correct side of the lens. So what that means is that the object is on one side, here's the lens, the image is on the other side. If I got DI was negative, and it's a lens, then the image and object are on the same side. Now, the reason why I say the right side here is that when it's a mirror, it kind of goes the other way. Mirrors are supposed to reflect light. So if I've got a mirror here and the object is here, positive DI means that the image is on the same side as the object because that's where the light is supposed to go. Negative DI with a mirror would mean that the image is on the other side, which is really in darkness. There's a wall there. All right? So that's what you should think about. DI positive means the correct side, the side that you would expect light to go. All right? So with a lens, it means you expect light to go through. With a mirror, you expect light to bounce off. All right, so that's with DI. Same thing with the focus. Focus is positive when it's a converging lens. And that means that the focus is on the opposite side of the lens than the object. It's negative when it's a diverging lens. And that means that light doesn't actually come from the focus or go through that focus. It only kind of pretends as if it came from the focus. All right, so that's the way that we need to interpret it. And those are the only tricky things. Now, we can also pull out of this a quantitative description of the magnification of the object. Magnification is defined as the size of the image divided by the size of the object. And it's also given by negative distance of the image over distance of the object. So what that indicates is that if the distance of the image is positive, which means that the image is on the correct side, then the magnification will be negative. And that means that real images must be inverted if you're only using one lens. If you're using two lenses, then you might be able to put yourself in a situation where the distance of the object is negative also, and then you've got a nice positive magnification. So two lenses, you can get an upright real image, but only one lens, If it's a real image, it's inverted. If it's a virtual image, it's erect or upright. All right, so let's do some examples. So over here, I've got an object that's 2 centimeters tall. So this is the size of the object. And it's placed 20 centimeters in front of a converging lens. So this is going to be my distance of the object with a focal length of 15 centimeters. So this is going to be my f. All right? Now, am I going to take it as positive or negative? Well, it's a converging lens, and so that means that my focus should be positive. All right, so let's just use the lens equation. So we'll say 1 over DO plus 1 over DI equal 1 over F. All right, so 1 over DO, well, DO is 20, so I'll do 1 over 20. I'm not going to convert to SI units here because everything's in centimeters. So I should just understand I'm looking for a length. It's going to have to be in centimeters. All right? You could convert if you wanted to, but I think the math looks easier without. Plus 1 over, I don't know that, so I'm just going to call it DI, equal 1 over F is 15, so I'm going to do 15. So that means 1 over DI is equal to 1/15 minus 1/20. All right, now if you go through that, you'll find that this is 1 over 60. The easiest way to do it is just type in your calculator. 15 to the negative 1 minus 20 to the negative 1 equals, and then answer to the negative 1, and you'll get 60. So this means that DI is 60 centimeters. All right, now, it wants me to describe the image, not just write down DI as 60 centimeters. So what I would say is the image is a real image, DI is positive, that is 60 centimeters on the other side of the lens from the object. All right? What about its size? Well, SO is 2 centimeters. All right? So that means that the magnification, which is minus DI over DO, is negative 3. So that means it's an inverted image that's 3 times bigger. So it's going to be 6 centimeters tall, but upside down. All right? And so that's the answer to this guy. Not that bad. The problems come in when we don't do this math properly. So if you ended up with negative 5, that's a problem. It's not 15 minus 20. It's 1 over 15 minus 1 over 20. And then we have to do 1 over that. Kind of annoying, but I don't know what to tell you. That's the way the equation works. All right. So let's look down here. The next example is everything's exactly the same, except it's a diverging lens this time, not a converging lens. All right. Well, what's the difference between a converging lens and a diverging lens? The difference is that the focal length should now be taken to be negative. So we'll start off with the same equation, but then when we plug in the numbers, it's negative 1 over 15. And that changes everything, because now it's 1 over DI equals negative 1 over 15 minus 1 over 20. All right? So that, if you type it in your calculator, you'll find that DI is negative 8.57 centimeters. Not as nice as it was before. All right? So now what we would say is that the image appears on the same side of the lens as the object. It is a virtual image. It is 8.57 centimeters away from the lens, which is much closer to the lens than the object. Now, a nice, easy thing to remember is that whatever's closer will be smaller. So since this image is closer to the lens, it's going to be smaller, and that means the magnification will be less than 1. In fact, we can calculate the magnification. Magnification is 8.57 divided by 20, because it's negative distance of the image over distance of the object. And this is 0.4286. All right? The magnification is positive. That means that it is an erect or upright image. All right? And the size of the image will be equal to this times the size of the object. So it's going to be 0.8572 centimeters. Okay? Which is certainly less than the size of the object. And that's the lens equation. Most important thing to remember, it's 1 over DO plus 1 over DI equals 1 over F. That, and also what does negative distance of the image represent? Remember that that always represents that the image appears on the wrong side, whichever side you do not expect light to be on. That's the side that the image is on. It's always a virtual image when DI is negative. And that's the lens equation.